So in this video we're going to show a worked example of solving a second order linear homogeneous differential equation that has constant coefficients. In the case where our characteristic polynomial has two real roots. And what we developed in video 2 was the idea that if we have a second order linear differential equation with constant coefficients, that we could find the characteristic polynomial for it, ar squared plus br plus c. And if it has distinct roots r sub 1 and r sub 2, we find the solution by doing y equals c sub 1 e to the r sub 1 x plus c sub 2 e to the r sub 2 x. So this is just on here so that you can remember the solution process that we derived in video 2. So you start with your second order homogeneous linear differential equation with constant coefficients, and you create the characteristic polynomial. So our characteristic polynomial is going to be 2 times r squared minus 3 times r minus 2, and the characteristic polynomial has to be equal to 0. So we're trying to find solutions to our characteristic polynomial. So the easiest possible scenario is when there are two real roots and you can figure out how to factor and find the roots by using the zero product property. So in this case, 2r and r would be 2r times r is 2r squared. And then I need a minus 3 right here, so I might try a minus 2, because 2r times minus 2 is minus 4, and then probably a plus 1 right here. So 2r times minus 2 is minus 4r, plus 1r is minus 3r, and 1 times minus 2 is just the negative 2. So I have it factored, and now I can go 2r plus 1 equals 0, or r minus 2 has to equal 0. So we get solutions r equals 2 and r equals negative 1/2. So we have an r sub 1 and an r sub 2, two roots, and we just want the linear combination because our guess was that y was equal to e to the rx, so we're just popping our r's into the exponent position. So our general solution is going to be y equals c sub 1 e to the r sub 1 x plus c sub 2 e to the r sub 2 times x. And of course, if we had initial conditions, we could try to find a particular solution by solving for the c sub 1 and c sub 2. Another way that you could have gotten at this, so I'll stop here. If you want to check out of this video at this point, that's okay. We could have used the quadratic equation, so we could have done r equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2 times a, and use the quadratic equation to get the solutions out of this. We could have completed the square on this. So any method that you know to find roots works. So if we had 2r squared, for example, minus 3r minus 2 equals 0, and then we add 2 to both sides and then divide through by a 2, so we'd wind up with a 1 over here, and r squared minus 3/2 r. We could have taken half that coefficient and then squared it and gotten 9/16 and added that 9/16 to both sides, which would give us r minus 3/4 quantity squared, and we get 16/16 plus 9/16, that'd be 25/16. And then we could have taken the square root of both sides and gotten our r minus 3/4 equals plus or minus 5/4. And so adding 3/4 to both sides, r equals 3/4 plus or minus a 5/4 equals 5 plus 3 is 8, divided by 4 is 2. And 3 minus 5 is negative 2 over 4 is negative 1/2. So we could have gotten the roots by completing the square. We could have plugged our pieces into the quadratic formula. So the solution is going to look like this regardless. If you get two distinct real roots, c sub 1e to the root 1x plus c sub 2e to the root 2x, and then the question really is how you're going to find those roots. Are you going to do it by factoring? Are you going to do it by completing the square? And of course, if the roots aren't nice, then you may have to complete the square or use the quadratic formula.